everyone, and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber. Today we're going to briefly talk about outliers and Frank Wilcoxon, that is to say, one of the fathers of non-parametric tests. Usual disclaimers: I'm not a statistician or an expert in statistical software, but I often like to play with stat software and statistics. Brief look at what we have done so far. We talked about assumptions. We talked about now a significant number of statistical tests, some of them suitable for normal distribution, some of them not. Particularly, we talked about how Spearman's and Kendall's correlations particularly are very useful when the data is not normally distributed. And we looked at how to run them. So today we're going to move on a little bit, and we're going to talk specifically about skewed data. And we are going to talk about what happens when you are comparing two groups with continuous numerical data, when the numerical data is either paired or non-paired. And to start with the example, we're going to start with non-paired data. We're going to look at it using Jamovi. So let's start our story, which is probably the most interesting part of this presentation. So Frank Wilcoxon was a chemist, and he was doing some experiments back in the days in his lab, and he managed to get his hands on a particularly famous book at the time, which was Fisher's book on how to conduct a scientific experiment. That sort of very famous book that we talked about, that introduced the concepts of randomization, etc., etc. And he realized that a lot of the things that were written on that book were actually not working very well for him, because he was dealing with an environment where things were not sort of always happening in a fairly controllable way. Whenever you're dealing with a chemical reaction, you've got lots of things that can change the way a particular reactant interacts with an enzyme, and the speed by which the reaction happens can be affected by gajillions of variables. Most noticeable: temperature, presence of catalyst, contact between the elements, concentrations, pressure, and so on and so forth. Conditions that are very, very different from a crop, which is where most of the statistics that Wilcoxon were dealing with actually originated from. If you remember, for example, Students T was coming from studies on crops. A lot of the early studies that were published by Fisher were also on crops. So a very, very different environment. And he couldn't quite work out why the statistics he was trying to use on the experiments he was running were not working. So he very quickly realized that he had two problems. One problem was outliers. Whenever he was doing a reaction, he would do perhaps 3 or 4, 5 of these reactions with the same amount of chemical A, a same amount of substance B, and obtain very, very different levels of substance C. Or he was obtaining substance C at very different speeds, to the point that some of the results that he had were completely off the chart. And he couldn't quite work out why, and he couldn't quite work out why this was affecting the statistical test he was running to determine differences between these samples, why it was affecting them so much. And he pretty quickly realized that some of those results, that is to say outliers, were significantly affecting his calculations. That's one of the main problems he had. The second problem he had was the distribution. So the vast majority of what was published at that point was based on a normal distribution, and he certainly had a very abnormal distribution. paranormal this vignette would suggest. So he set off to resolve this problem. And the first problem he had was, well, what's an outlier? Difficult to say. Interestingly, there is no universally sort of recognized definition of an outlier. This is Stephen Hawking's definition of an outlier, which, as you can see, is very generic. You could apply it to pretty much anything, from chemistry to crops to boyfriends, as you can see in this lovely vignette. By the way, if you're interested in where these vignettes come from, it's a lovely website. You can snap the QR code on the bottom left. It's really funny if you like these type of things. So let's go back to our previous vignette, outliers. No clear-cut definition, but there is a way to kind of define them, or at least visualize them, and that is to say the box plot. Box plots have been around for bonkers years, and they're still very underutilized in data representation, both in medicine and outside medicine. The vast majority of box plots and the softwares that do make box plots, including Jamovi, will flag up when a distribution is affected by outliers. And the definition of outlier in the classic representation of a box plot is anything, and you have to follow me for a second here, that lies 1.5 of the interquantile range above or below, respectively, the third or the first quartile. I hope that makes some sort of sense. So if you look at this box plot, for example, we could see that this kind of contains a graphical representation of sample. This is the third quartile. This is the first quartile. This is the median. This is the max. This is the min. So if there were to be data that sits more than 1.5 times above this point in comparison to this block, it will be flagged up as an outlier. You can see it here because these 2 points lie well above 1.5 of these. Okay? I hope it makes sense. Feel free to interrupt me if it doesn't. And that's a very simple way to figure out whether your distribution, the data you're analyzing, has got outliers or not. Outliers and the tendency of a distribution to have outliers is sort of defined as kurtosis, which is another way of determining whether your data is prone to have outliers. And kurtosis has to do with how spread out the tails of your distribution are. Okay. This terminology, I must say, I've never actually seen it used in common jargon, but basically this is a flat, this is an average, and this is a very tall with relatively limited tails distributions. Remember that it doesn't matter how tall this is, it's the tails that make the difference, okay? Kurtosis can be calculated, and this is normally said to be above 3, and this is said to be below -3, I seem to remember, or we'll have a look at it in the software in a minute. Obviously, normal distribution, which is, again, the most important concept here. And this was the other one of the problems that Wilcoxon was facing. So one was crazy outliers, and we kind of talked about how you pick them up. And the second one was a normal distribution. His distribution was very abnormal. And how did he get around it? Well, very similarly to what Spearman did in his rank correlation. So he designed a test to compare 2 groups of continuous variables. Instead of using the actual value, he would use the rank that value take in the distribution. And this is just an example, the same that we used a few weeks back. We have a number of plants. Each plant has a certain height, and each plant produces a certain number of grams of marijuana. That is to say, no clue if this is actually in any shape or form accurate for real life, but anyway. So as you can see, the numbers are very different. So this is 45 centimeter, most certainly would be an outlier. And you can see if you were to plot it in a normal plot, having plant height on one side and produce gram on the other side, you would probably get a crazy intersection point here. So in order to kind of make the data sort of more digestible to a statistical test, instead of using these absolute numbers, you can use the rank. And in this particular case, 25 centimeter will be rank 2 because it's the second value from the bottom. 23 centimeter is rank 1. 27 centimeter is rank 3. 45 centimeter is rank 4. The same goes for the grams. So you can see that because this is the biggest number of grams and this is the highest value you get on the plant, they both rank 4. And if you think about it, you can imagine how ranking variables kind of transforms your distribution into something that's a bit more normal or a bit more handleable, if that makes sense, especially if you're dealing with massive numbers. Like think about comparing, I don't know, the populations of different countries, United States versus UK. Obviously, the United States is massive. If you put all the countries of the world, you'll have a few that are at the top with millions and billions of population, and the vast majority will be in the middle. So those will be outliers. If you rank them instead of using the absolute number of people that live in there, you will probably get a more sort of accurate representation of the statistical relationships between various countries, if that makes sense. Just a quick note, the Wilcoxon rank sum test, which is sort of what we discussed so far, is also called Mann-Whitney U, and it does deal with independent samples. So two different populations with two different sets of variables. The Wilcoxon signed rank test, on the other hand, is the equivalent for non-parametric of the paired students T. So it deals with paired sample, where you have a measurement taken at time 0, an intervention and measurement taken at time 1, such as blood pressure pre and post treatment. I hope that makes some sort of sense. So to give you a practical example, we'll go back to my dissertation data set, which we've used now pretty much in every session. If you recall, for this particular study, I collected data about papers that were advertised on Twitter by publishing journals. And today we're going to look at retweets data, and we're going to try and determine whether there's a difference between medical and surgical papers in terms of number of retweets that the papers get. So let's have a quick go. Unless you guys have any questions before I fire up Jamovi.
So, quick question, Gio.
Yeah.
So the Wilcoxon's rank sum test
Yes.
is the same as Mann-Whitney? I hadn't realized that before.
Yes.
And it's different to the Wilcoxon's sign rank test because obviously that's for paired data, yeah?
Yes, correct.
Okay. Thank you.
In Jamovi, let's start by doing a bit of box plotting, because I think Jamovi does it really well and does it very quickly. So the problem I found when I was looking at generating box plots in this data set is that the values I've got are very significantly affected by outliers. So it's nearly impossible to find a decent looking box plot. They all look like this. Let's have a look at this one, for example. Yeah, a bit better. So you can see how this box is the interquartile range. The median is in there. And you can see how everything that's 1.5 of this above it is flagged as an outlier. Also, Jamovi is quite smart, and obviously the density of this plot is massive, but it does flag you what row in your data set the outlier is. So you can go and find it if you want to, and explore why it is an outlier. So it is very, 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 very easy to do box plots in Jamovi. Don't try and do them in Excel, it's a mess. See if we can get one. That's nice. No, they're all pretty much the same. That's because my data is very abnormally distributed and it's got a lot of outliers. It's just the way the data is. You can take the labels off if you want. And it does also tons of other plots if you want to. But today, for the purposes of defining outliers, we're going to stick to that. Now, let's move on to the Wilcoxon test. Unfortunately, it is labeled under t-test for whatever reason. You have to go onto independent samples t-test. And we said we were going to look at retweets, so let's do that. Don't worry about the extra bits on the label. It's something I've generated some time ago. And we split it by grouping variable. And as you would expect, the first thing it does, it gives you students t-test. It also tells you that the variances are different. But here you can find the Man-Whitney U-test. Can remove the students T. So it's very easy to run it here in Jamovi. And you can then also run additional statistics. Very importantly, normality test. We explored this last time, a few sessions ago. This data is not normally distributed, and Jamovi tells you quite quickly. You just have to check normality test. It also gives you an homogeneity test. If you remember, we talked about this, the Levens test. So the variances between the two groups are very different. That's it. Not much else to add. Thank you, everyone, for tuning in and listening. Until next time, keep running your life with our surgical